Question number 25. We have a collision of two objects here. One is more massive. The 2m right here is at rest. M starts with what we see is a potential gravitational energy. There's frictionless surface right here. Fortunately, we're not losing any energy, supposedly. And that gravitational initial energy turns into kinetic energy here, I can say final, for m, right before the collision. We need to figure out the common speed after the collision if the packages stick together. That means that the collision is perfectly inelastic. And then in B, it gets a little more complicated. They're saying that it's perfectly elastic, which means kinetic energy will be conserved. And another thing, as you remember from our lab, approach velocity equals separation velocity. Let's start with A. First off, A or B, we need to figure out the speed of package M right before the collision. So that's what we're going to do first. mgh initial equals mv final squared over 2. Blissfully cancel M. And then the v final right before the collision for the first object is going to be root of 19.6 times 3, 7.67 meters per second. That is the speed of this object right before it collides with 2m. Then we're going to talk about conservation of momentum. A, perfectly inelastic. We start with m times 767 should be equal to 3m because they stick together times v final. So it's 767 divided by 3, 256 meters per second. So that would be the answer to A. That is their common velocity, 2.56 meters per second. That is how fast both of them, after they stick together, move to the right. If it is a perfectly elastic collision, this one being lighter will bounce back to the left, and the 2m is going to go to the right with a slower velocity than 767, granted. And we need to figure out what height does the package of mass m rebound to. Basically, we need to figure out the final gravitational energy, right? So two things. Just writing down the conservation of momentum. I will say 767 m, that's the initial momentum, should be equal to conservation of momentum. So it's going to be mv final plus 2mv final. And I'm going to say 1 and 2. That is the conservation of momentum. Technically, I should say vectors in here as well, right? And then think about this. One is at rest and the other one is approaching it at 767. That is the approach velocity to the right, and it equals 7.67 meters per second. The separation velocity, I'm going to also make it to the right, and this will be v final 2, and I will subtract v final 1 from it. So 7.67 should be equal to v final 2 minus v final 1. V final 2 equals 767 plus v final 1. And now I'm going to substitute. 767 times the mass equals mass times v final 1 plus 2 masses, 767 plus v final 1. And I dropped the direction of vectors for now. Mass can go. Then I have 7.67 equals v final 1 plus twice 767 plus 2 v final 1. So then v final 1 3 times equals negative 767. From where v final 1 is negative, what do you know? 256 meters per second. So it bounces back with the velocity that was equal to their shared velocity in A. And then we are after how high it gets. So gravitational final should be kinetic initial, and kinetic initial, mind you, this is after the collision for our M. And then you just do mgh, and we'll go equals mv initial squared over 2, from where h final is going to be 256 squared over 19.6. 0.33 meters, so 33 centimeters is going to go back up.